Hello everyone, welcome to our work. We demonstrate that in a social media platform, the service providers are able to recover detailed user preferences from publicly available aggregated statistics, which can be a threat for user privacy. Social media platforms such as Facebook, Instagram, or TikTok rely largely on their personalized content recommendation algorithms. To optimize the recommendation algorithm, they usually ask for user identity information, and they collect detailed user behavior or preference information. On one hand, as a customer, we are receiving more personalized and entertaining services, but on the other hand, our detailed sensitive data are facing a high threat of being abused. More recently, we have seen increasing frequency of online data breaches. And due to the heavily optimized or personalized recommendation in these social media platforms, adolescents' addiction issue has further stimulated the discussion about how to properly use our data while protecting our privacy. A traditional way of protecting user privacy is through aggregation. The individual level storage of sensitive information, such as user preference, is prohibited. Instead, only the aggregated statistics are kept, such as the total reads of articles or the views of videos. Such statistics are publicly available. However, as the content provider on social media platforms is transforming from users to the social platform itself, such as the short video app TikTok, the social platform has gained a high degree of centralization, which can make the aggregation an ineffective way of protecting individual user privacy. Specifically, the service provider can actively choose which content to push to each user. This makes it possible to design special pushing algorithm so that the aggregate views of the content contains complete information of each user's preferences. The service provider can claim that they protect user privacy by only storing aggregated reads, but in fact, they can still recover the detailed user preferences to optimize their algorithm. In the social media platform, each user is pushed a set of articles of one topic. The users who are interested in this topic will read all the articles. Those who are not interested will simply skip all. For each article, the total number of reads is then collected and stored. Our goal is to design a push algorithm so that the user preferences can be recovered. Specifically, we want the push algorithm to have the following properties. First, each user is pushed a small number of articles. And the inference algorithm should be of low complexity because when the system is large, the number of users in the system is very huge. We want to use as few articles as possible. We formulate our problem as the user preference compressing and recovery in a bipartite graph, where there are m article nodes and n user nodes. Each user's preference is represented by a binary variable, where the epsilon proportion of users are interested of this topic, so they have a preference equal to 1. An article is pushed to a set of users, and the corresponding article node is connected to their user nodes. So the bipartite graph structure depends on the design of the pushing algorithm. The aggregate reads of each article is computed. It is equal to the total number of interested users who are pushed this article. Our goal is to recover the user preferences for all the users while minimizing the article-to-user ratio beta. This problem can also be formulated as a class of compressive sensing problem, where the signal x is an n-dimensional binary vector representing the preferences for n users. However, in the worst case, the compressive sensing have a complexity in the order of n to the power of 3. Though it is polynomial, it can still be too slow for a huge system. Another related work, Counterbridge, studies the compressing and recovery of network flow, where they proposed an inference algorithm with linear complexity. Counterbridge uses a k-regular graph, and the network flow takes value in an infinite alphabet. It is able to prove an optimal counter-to-flow ratio, which is equal to 2 times square root of epsilon, where epsilon is the number of flow that is larger than a minimum flow size. In our setting, we can design the inference algorithm which can achieve the linear complexity. And since the user preference only take value in 0 and 1, and we don't limit our pushing algorithm to a certain type of bipartite graph, so we can prove an optimal article to user ratio that is equal to square root of epsilon times 1 minus epsilon. Our inference algorithm is based on message passing, where the user message represents the estimation of each user's own preference, and the article message represents the estimation from the article's perspective. The messages are passing between users and articles to update the estimation of user preferences. Specifically, the estimation of user preferences are initialized to their lower bound, 0. The article node collects user message and compute its estimation of each user by subtracting the estimation of other users from its own aggregate raise. In odd round, the user estimation is the lower bound of their own preference, so the article estimation is actually an upper bound of the actual user's preference. Similarly, in the even round, the article estimation is a lower bound of the user's preference. Then the estimation from the article's perspective is projected to a valid user preference value range, 0 to 1, and then sent back to the users. Upon receiving messages from the connected article nodes, the user node will pick up the most accurate estimation as its new message. With the proper pushing algorithm, as the iterations goes on, the upper bound in the odd round and the lower bound in the even round will coincide to the true preference of the users. We formulate the push algorithm as designing the bipartite graph structure. To formally analyze the performance of a bipartite graph, we design the edge perspective degree distribution function, lambda and rho, for the bipartite graph. Each of them is a polynomial function where the coefficient for the kth term is the proportion of edges with degree k. The article of user ratio, beta, can be also represented as a function of the degree distribution. With the expression of the degree distribution, we can formally define the error evolution during the message passing inference algorithm. Note that in the odd round, the messages received by a user node is an upper bound of its preference, and we projected the message to 0 and 1. So only when a user with a preference 0 can have a wrong estimation. Similarly, in the even round, only when a user's preference is 1, it can estimate its own preference wrong. So the error in the odd round is multiplied by a factor of 1 minus epsilon, and that in the even round is multiplied by the factor epsilon. We concatenate the evolution of an odd round and an even round, and we get the recursive error function of 2 rounds. Our model is similar to the binary erasure channel. Given a target erasure rate epsilon, we can construct a sequence of capacity achieving graphs where the error function will converge to 0 in the message passing recovery algorithm. This graph can achieve an optimal beta equal to epsilon. Comparing to the binary erasure channel, our error function is a concatenation of 2 iterations. Our pushing algorithm is designed based on the capacity achieving graph using square root of epsilon times 1 minus epsilon as the erasure rate. We can prove that our function of the 2 iterations will converge to 0, and we can achieve an optimal article to user ratio beta that is equal to square root of epsilon times 1 minus epsilon. Moreover, we are able to prove the existence of the phase transition phenomenon. When the graph is designed for the proportion of interested user epsilon star, then if the actual proportion of interested user epsilon is smaller or equal to epsilon star, we are able to recover all the user preferences reliably. But if epsilon is larger than epsilon star, some user preferences cannot be inferred. This proof is not trivial because our error function is not monotonic in epsilon. In the inner iteration, it is decreasing with respect to epsilon, and in the outer iteration, it is increasing. But we are still able to prove this property for the capacity achieving graph in the limit case. We run the experiment on the capacity achieving graph to verify its optimality. We tested 4 families of graphs with various n. The system contains 10,000 users, with 10% of them interested in this topic. We can see from the figure that the graph with n equals to 30 or 20 achieves the zero reconstruction error at beta equal to 0.34. It is the lowest among all the simulated graphs, and it is approaching the proved optimal ratio, which is equal to 0.3. Next, we simulate the performance of a given graph which is designed for a specific proportion of interested user, denoted by epsilon hat. We tested 3 families of graphs with epsilon hat equal to 0.1 to 0.3, and we vary the actual proportion of interested users, epsilon. We observed that for all 3 families of graphs, when epsilon smaller than epsilon hat, the reconstruction error are close to 0. That is, the graph designed for a specific epsilon hat is capable of recovering user preferences for all the scenarios with a smaller proportion of interested users. The reconstruction error increases fast when epsilon is larger than epsilon hat, which is consistent with the phase transition result. We further simulated the k-regular graph where each user node connects to k random articles. We tested 5 families of k-regular graph. From the figure, we can see the families with k equals to 3 and 4 achieves the best performance. The convergence error goes to 0 when beta equals to 0.34, which is also very close to the optimal ratio. This makes the k-regular graph a very practical choice because each user only needs to read a small number of articles, and the recovery power is also strong. Next, we simulate the performance of a given 3-regular graph designed with an article-to-user ratio beta. We observe that for each beta, there exists a transition point. When epsilon is smaller than this transition point, the reconstruction error converges to 0, and above this point, the reconstruction error increases. Note that for the k-regular graph, we are able to compute the proportion of interested user epsilon by dividing the total count of all the articles by k. This enables us to select beta such that epsilon is less than the corresponding transition point, so that we are able to reliably reconstruct all the user preferences. In conclusion, we proposed a push algorithm and an inference algorithm that infers user preference reliably. This algorithm can achieve an optimal article-to-user ratio beta equals to square root of epsilon times 1 minus epsilon, which is very close to that of compression syncing. In addition, we demonstrate the phase transition phenomenon, which helps the design of pushing algorithm with the estimation of the proportion of interested users. Thank you.